Okay, so this comes in the heels of last week's theme, which was functions, and this week I'm going to cover objects, which are tends to be viewed as very different from functions, but as I already kind of hinted, to some extent you can definitely model functions as objects because we've done that. That's what object-oriented programming languages do when they encapsulate functional elements. You can also model, to some extent, objects with functions, although not entirely, and I will tell you what the limitations are. So let's get going here to the presentation. And I assume that all of you know OOP to some extent. You've coded in whatever, Java, OO, Python, C++, C#. It's kind of hard not to use an object-oriented programming language these days. So I'm not going to talk about object-oriented programming per se. I'm going to talk about the obscure corners of OOP. And the things that perhaps you know, perhaps you never really had time to think about much. So we'll talk about encapsulation, we'll talk about classes versus a lot of alternatives that had been bounced around when people started designing object systems. And they still exist in some languages, as you will see, some of these alternatives. Code reuse, dynamic dispatch, the self-reference, and so in different kinds of flavors. Okay, so these are it's a eclectic set of topics related to OOP, not just OOP, the base OOP that you already know. So let me talk about the encapsulation, because that is the beginning. That's where objects start. So previously in structured programming, which was the big move away from GoTos, we had in languages in the 70s like Pascal or C or something like that, we had data that was passive, and then we had procedures or functions that were encapsulating sort of the algorithms that manipulated the data, right? So that's where we were in 1970, something like that. This is also where the concept of an object emerged. So the first object-oriented language, which was a modeling language, was Simula, and it was designed and implemented in 1968, a little actually earlier. So the first reference was Simula 68. So the language itself had been in development for a few years before. So and as I said, Simula was designed to be a simulation language, not necessarily a general purpose programming language. It was to express real world scenarios, right? So the idea that you have, basically for operations research or something like that. So you have real world objects, transportations or whatever products, and people have to express or specify the models for those processes. Right? And so objects seem like a good match because you have sort of objects in the real world. So we wanted to kind of capture that in the language too. But the interesting thing, as you know, about objects is, in case maybe you know, maybe you haven't never stopped to think about it, is that an object contains both the data and the functions, right, that manipulate that data. Okay, so an object is a little capsule. That's the essence of an object. It's a capsule that wraps around state, right? It contains states, and the way that you change states from the outside is by invoking certain procedures that belong to the object itself. So in principle, and this is the model of, the theoretical model of objects, you don't access the data directly. You invoke methods on the object, and then those methods may change the data, but that's invisible. That's the principle, right? Now, different languages these days have different kinds of visibility to access the data of the object, but those are details. So an object does things according to the model of the real world, right? So you have a car that moves or that brakes or that steers. So an object is defined by the things that it does. And it's responsible for its own data, but it can expose the data through other objects, through the public methods that it provides to the outside world. So that's the idea. So objects were this new thing that came around that kind of unified or kind of made a unique concept out of the previously separated data and functions that were all over the program code. So they just, okay, here's a little unit, has its data, and these are the methods with which you can change that data. Only these methods can change that data. So I'm going to skip this because this is OOP 101. So, but the main thing about objects that sometimes gets forgotten in many programming languages, most notably Python, is that the data is supposed to be private to the object. That's the principle of objects. So you should not access data directly from the outside. Now, Python does not have any accessibility parameters, so you can just access anything that is defined in a class. You know, through a class, you can access all the data that is defined in there. But the idea is that the object should follow the principle of information hiding, that they should hide everything except the things that are absolutely required to expose, and those should be methods, not data. So your class is responsible for its own data. Don't allow the classes to access it. So, and the advice then, the corollary of this advice is that rather than accessing the data directly, you should provide these getters and setter methods that access the data. Basically, they provide an extra layer of abstraction on top of the data, also because they're very convenient, because sometimes just the fact, you might think, okay, so what's the point? If you just have getters and setters to read and write the methods, the data, why not just let access the data anyway, right? You may think about that, and sometimes maybe that's what you are thinking when you make the decision to make some field public. But the idea is that you should think about the other way around, that everything should be private. All fields should be private. Okay, and then if you really need to change some field, it should be done through a setter method that may actually do more things than just change the value of the field. It may make some some checks about the new value that is being given. It may have other side effects, change other things. So the setter encapsulates the update of that particular field, but it may make a lot more other things, not just changing the value. So it gives you an opportunity to redefine what does it mean to change the field. Right. So the object maintains control if you continue to have these getters and setters. So Java provides, and Java in C++, I think, provides, and C# provide these public, protected, and private levels of access of the fields. So in small programs, this isn't so important, but if you're just doing a little program that of 100-line program, it's not so important. But if you're working on a large code system, visibility is really important. And again, you should start by thinking that everything should be private. Okay, but that should be the default, not any other thing. So the default says everything should be private. Only when you actually need to change something, then you should consider giving it a setter of some sort. Okay, so, but now I am going to talk about different flavors of objects that are a little bit more off the beaten path. So One of them is the small talk style of objects. Pardon. For those of you who don't know, Smalltalk is a very old language. In fact, it was the first real object-oriented language that came immediately after Simula. So Simula, as I said, was a simulation, modeling and simulation language. It wasn't really a full-blown programming language, but soon after Simula, in the early 70s, people at Xerox PARC who were working on the first personal computer started designing this language to program that personal computer that was called Smalltalk, and it was highly inspired by Simula. So Smalltalk it comes from the early 70s, and basically took Simula and made it a full-blown programming language. So what would objects wrap around data? Another interesting thing is that in Smalltalk terminology, objects were really independent units. So they were not just, so they didn't just wrap the data, but they were supposed to be independent units. So the way that you invoked something on an object was by sending a message to the object. So there was literally that kind of metaphor, that concept that objects were completely separate things. And the way that you interact one object with another is by one object sending a message to another object. And then based on that message, then that object would dispatch it and do something, invoke a method. But there was the concept of a message that was being sent. So the way that once the object receives that message, something is looked up, right? Do I have the capability to understand this message by means of having a method defined for it? And if so, then you look it up and you execute that method. And this dispatch was dynamic, right? So Smalltalk was an interpreted language. So the method dispatch was dynamic, meaning that if you sent a message that the object didn't have a method for it, it was only when you sent that message and then during the dispatch that it realized that it didn't have a method for it, then there was an error, message not understood error. So this is more or less the model of chapter 12 of the book, which is, I believe, one of the exercises. Let me make a pause here and just go to the assignments this week. Right, so chapter 12, which is the letterbox. So the letterbox is very much inspired in the Smalltalk model, although as some of you may see some similarities here with another language that is perhaps more used these days, which is called Erlang. Erlang is a language for distributed, highly distributed concurrent applications, and uses a model that is very similar to this one, but it adds threads into the mix, okay? I don't want to talk about threads. I will talk about threads a few weeks from now, and I will mention Erlang again. We will revisit this style in the context of threads. But this particular model of objects, we're still not talking about multi-threading programs or anything, but the idea here, if you see what is going on, for example, so now we're in the object world, right? So we divide the problems into classes of objects, right? So we have, the data storage manager, we have the stop words manager, we have the word frequency manager, some controller over here, right? So we're dividing the problem into an object-oriented design. But if you look into each of them, they all follow a little bit of the same pattern. Look, they all have a dispatch method. So that's a very important dispatch method. This is such the receiver of messages. Okay, so this is the method. This is the only public method that the objects have. Okay. It's the only public method that the objects have. They only have the capability of dispatching messages. So they get a message and then they look at the message and what is this message? Is it the init message or a word message or something? And if it is, for example, the init message, then I run the init method over here. Otherwise, if it's this words message, then I run this words method over here, right? And the way that objects interact with each other is by sending messages. Let me see if I have message being sent somewhere here. I don't, but here, let me see. Stop word manager, here, word frequency manager. Here, for example. So data storage manager dispatch, which is like the send message, and that this is a little message, right? So the way that I'm modeling messages here in Python is just little pairs of things. The label of the message, and then some data if it needs arguments, right? So again, this is in Python, so I'm using a very lightweight data structure that's just a little, I'm using a list, it could be a pair, but a tuple, it could be a tuple, but I'm using a list over here. If you do this in other languages, you may want to actually model the message itself as a class, a nice class that has the label of the message and then some data. But so this is supposed to be the message, right? And then the message is then dispatched, and then the right method is run. Okay. So in this model of objects, basically all objects have the capability of receiving messages. That's all they do. They can receive messages, and what are messages? They are little data structures that have a label, which is the name of the message, and potentially data that's going to be the arguments for that message. Okay, that's it. So forget about those methods that you define in Java and C# and Python and all that stuff. So this model is a lot more primitive. It's a lower level that you just have this dispatch method. That's the only thing that the objects can do. Okay. All right, so this is chapter 12 of the book, Inspired by Smalltalk. Now, the one thing that characterizes object-oriented programming and objects in general, and even when they started, actually the model for objects, but they are wrappers of state. They are holders of state. They're supposed to hold on to state. That's what we see in the world, right? So we look at the car, and it's the same car, even though it's moving, right? It's changing its state, it's changing its position in the world. The car is the same object, right? So basically the concept of an object came in on purpose to capture the concept of state, of something that holds on to, changes but holds on to state, and holds on to that state that is important to it, as opposed to all other states of the world, right? So a car has some state, it's changing as it executes, but it's the same car, right? It's not a different car when it moves position, okay? So objects are immediately and explicitly and unabashedly imperative, okay? They are side effectful. That's what they were designed for. That's what objects were designed for, to kind of trying to mimic the way that we perceive the world. Whether the world is like that or not, we don't know, because that we would have to ask a physician whether every time that we make another change, it's really still us or it's a copy of us. Maybe it's just a copy of us. Because this leads you to the next thing, because objects can also be stateless, right? And in fact, if you try to emulate objects with functions, pretty much in functional programming, pure functional programming, you cannot have states. So the only way that you can emulate objects is by having stateless objects, which means that every time that you want to change the value of something like the position of the car, you don't change the state of that car. You make a copy of the car and change. And the only difference between the original car and the copy is the position field, right? So you can always reproduce, copy the objects, and at the moment of creation of the copy, you change only that one thing that has changed, right? So that's a model of stateless objects, which is perfectly fine. In fact, there are many. There's some patterns out there in the world in large software systems these days that are object oriented that you tend to do stateless objects, and there's many good reasons for having stateless things in general, okay? Because then if you don't hold on to states, there's all sorts of things, it's a good things that you get by free, which is that, if you have a reference to an object, once you get that reference to that particular object, you know that that object is never going to change, right? That object is not going to change its position, never going to change, basically. So it's a good thing for testing, for multi-threading, for all sorts of good things. But nevertheless, there's a tension, okay, between the object-oriented world and the functional world, and it's a foundational tension. And I think it goes back down to physics, honestly, which is that objects were designed, were brought into programming world to cope with state, right? With this perception that there is state in the world that we want to capture and express. And functions are the opposite. Functions they're basically saying there is no state. There is no state at all, okay? It's an illusion. And if you want to create the illusion of state, then what you need to do is to create copies of things. And that's how the world unfolds, through copies of things. Which is a very fine philosophical discussion, I guess, at this point, until the physicists tell us exactly how the world is being done. But nevertheless, objects are designed to address our perception that there is state in the world, okay? And that's what we want to capture in our programs. So there's lots of, out there on the internet, there's lots of wars, tug of wars between people who are fans of functional programming and people who are fans of object-oriented programming, and especially lately on people who are being sort of discovering the benefits of functional programming, bashing on objects and the fact that they are stateful. So you'll see a lot of those discussions out there on Reddit and Hacker News and stuff like that. But that's how it is. Objects are valuable, and they were designed to capture our perception of the world, which means that we think that there is state that we want to capture in the program. So now let me turn the page and talk a little bit about the way that we program objects. The notion of a class is a weird notion, all right? Let me tell you already this. And most of you may have come to object-oriented programming by immediately getting familiar with the concept of a class. But classes aren't even necessary, and sometimes not even desired for having objects. Okay, so you can perfectly have objects without having classes. And in fact, there are lots of other alternatives. So let me talk about classes. Are a concept that has many hats. It has lots of different purposes. It's an object factory. Now I'll explain a little bit more. It's a type, and it's also a repository of things. So let me go through these three roles of this class concept that is really weird. And I'm talking about classes like in Java, for example, C#, even Python, okay? So a class is like a template or a cookie cutter, a factory. From a modeling perspective, right? The class describes a set of objects that all behave the same. That's what the class is, right? So let me not use the word type. It's a template right? It's a template in the sense that it describes how these objects are implemented. What fields do they have? What methods do they have, right? So it's basically how you use the classes, you even use the classes constructor, right? To create objects of that class, right? So a class is a little factory for objects that are the same. In most programming languages, a class is also a type. So when we go and talk about the types of the programming language, the user-defined types, the classes are usually types, all right? So every object belongs to a class, meaning that the type of that object is the type that is defined by virtue of defining that class. But it's two things, okay? Again, you could have types without having classes. You could have classes perhaps without having types. So the two concepts are related, but are not exactly the same, okay? This is what I'm saying. A class is many things. So it's a type too, but it's a template too. And finally, it's also a runtime repository of methods. So at runtime, the class has, when you call a method on an object, that method needs to sit somewhere, right? It needs to be somewhere. And then so the way that languages are implemented is that they are in data structures that correspond to directly that translates the class, right? So when an object is invoked a method, that method is looked up on that data structure. That's the class of the object. So a class is a weird thing that plays many roles in here. So let me show you the class as a repository of methods. What do I mean? So when you call some method foo on some object, the methods in many languages, now it depends on the language, so I'm going down into details, but in languages like Java and Python, C#, and most object-oriented languages, the methods themselves are not in the object. The object is actually just the data. It's a copy of the fields. That's basically what the object is. But as part of that data, there's a pointer or a reference saying what class does this object belong to. So there's a pointer or reference to the class of this object. So when on the object is evoked a method, then there's a lookup of that method, not in the object, but on the class of the object. And if it's here, then it's found. If it's not on this class, then it looks up through the class hierarchy. Right? So it may find it on some superclass, right? And this is finally the method that gets executed. But the classes are repositories of methods. That's where the methods are in most object-oriented programming languages. Not all, as you will see. I'm going to talk about some that don't do this. But this is the case in C++, Java, C#, Python, you name it. So now let me talk about languages that don't do that, okay? Those are interesting languages. Those are languages that are object-oriented, okay? They have objects, perfectly first-class citizens of the language. They just don't have classes, or maybe they use classes in a slightly different way. So this is the idea, the concept originally is called prototypes, okay? What are prototypes? These are objects, as the name says, that carry their own code. Okay, they're prototypes, meaning that it's just one-off, right? They're one-offs. They just encapsulate their own thing. So the important, as I said, going back to the beginning, the basics, objects are capsules of data and methods, right? And functions. Data and data are encapsulated. The way that most object-oriented languages kind of evolved from there was that they immediately added the concept of a class. That was the one that was defining all those methods and stuff. But some other languages actually in the 80s pushed back on that and started doing these these objects that carry their own code. And so you could have, when you define an object, you define an object, the fields and the methods for that object alone, not for any class of objects or any group of objects. Just one, you define just one object and then you define another object, and you can copy, right? You can start with an object, make a copy of that object, including the methods, and then you can change even some of the methods, right? You can extend, you can add more methods, all at runtime. So those are the prototype languages. Self is an example. So this is chapter 13 of the book. But another example is JavaScript. JavaScript is a really interesting language. You know, there's interesting things about JavaScript. There's a lot of not interesting and super confusing things. But I will talk more about JavaScript on Thursday because it's an interesting hybrid between objects and functions. But basically, prototypes are objects that contain their own methods. So here's an example of a prototype in JavaScript, okay? So here's an apple, and you can, you know, for those of you who know JavaScript, you can define just, you know, an object like this, okay? This is sort of a literal object. It has a field called type that is initiated to the string Macintosh, has a field called color that is initiated to the red, and then it has something called getInfo, okay? It has a field getInfo that actually gets down to a function, okay, a lambda. Okay, this is a lambda, an anonymous function. And so getInfo is, for all practical purposes, a method of this object, right? So you get to define it right here. And this is a method that exists only for this object, not for any class of objects, right? And there's a funky thing going on here with this reference, variable in JavaScript. Again, I will explain a little bit better on Thursday. But so you get, for example, apple.color, you can reset the color here by doing this, and you can call the methods by calling the lambda function that is bound to this particular name getInfo, right? And so this is an example of a prototype, which is an object that carries its own code, its own functions. And this is also chapter 13. So let me go here. I think this is one of your exercises too. So let me go here on chapter 13. All right. So this exercise is, I hope that you'll find this really interesting because this is inspired by a language called Self that you guys probably never heard of. It was an academic language in the 80s and 90s that had a lot of these ideas. But it's also very similar to the kinds of things that you can do in JavaScript for objects in JavaScript. So here's the thing. So in this model of objects, there's only prototypes, there's no classes, so objects carry their own code, and you define them just literally. So for example here, let me just show you, for example, here's the data storage object, right? And what are objects in this world? Objects are just maps, okay? The map data structure, okay? Key value pairs, that's what they are. Objects are just key value pairs, that's all they are. And some of those values are, you know, what we think as data, right? So here's a data that is a list. Here's another object here. Frequencies, that's a dictionary over here, right? And some of these fields are lambdas, okay? They are functions. So as I said, objects are maps where some of the keys are bound to data and some of the keys are bound to lambdas. That's what objects are, right? And so the way that you call methods on these objects is by calling these lambdas that are defined in here, okay? So for example, for W in data storage object of words, which is a function, right? So you have to call it, then you do something like that, okay? Now, there's one little extra thing that I asked you to do in this exercise. That's the exercise number 2. Let's move here. Right. So exercise number 2. Did I say number 2? Oh, I didn't ask you to do number 3. Number 3 is more fun. Okay, so number 2 is actually pretty simple. Let me see what I asked you to do. Maybe I'll add as extra extra credit. Right. So on week 4, yeah, okay. I only asked you to do 13.2. Okay, maybe I'll give extra credit for whoever does 13.3, because 13.3 is always fun. So let me walk through 13.2. 13.2 is just adding a method dynamically. Okay, so here's the thing: these objects are just maps. That's all they are. They're just regular maps. So if they are maps, you can add more key values at any point of the program, right? So the exercise 13.2 is to add an extra method sometime down, after you have defined the method. I don't remember anymore. What is it? Words with Z or something? Let me find it. No, top 25. A new method works called top 25, which stores the frequencies and prints the top 25 entries. Right. Instead of having the top 25 like this, you add a method and you call that method. You add a method to this word frequencies object right here, right? Not in the beginning, not when you initialize it, but later on, you add a new method, okay? And you call it. That is easy. Now, for those of you who want extra credit, and I will give it, and I'll put it in an exercise, 13.3 is a lot more fun. It's bringing the keyword or the concept of the self-reference, right? Because one of the things that I don't have here is the self-reference. So for example, look at this object over here, stop words object. So stop words object has a lambda, okay, that it's the one that checks whether it's a stop word, right? So it gets a word and checks whether it's a stop word. But in order to check if it's a stop word, it has to look up on this data, the stop word list that sits on this object. And so without the self-reference, this is such a little ugly because I need to call it by name, stop words object of stop words, right? Which is this thing over here. It's a little ugly. It'd be nicer to be just this, right? Dot or whatever, dot stop words or at least this, and then open brackets, stop words. Maybe bring this back. Okay, how can you bring the self-reference? How does the self-reference work? Basically, that's what I'm asking you to discover. How do object-oriented languages make this or the self-reference work? Okay, and they do it in the way that you have to do it here too. So think about it. I'll give it for extra credit. All right, so then we have abstract data types is yet another related concept in objects. Sorry, I'm dealing with some family emergency today. So abstract data types is something that exists also in modern programming languages like Java and C#. Not so much in C++, although you can definitely do them, or in Python you can definitely do them, but they don't exist as explicitly as in Java and C#. So abstract data types was something that was invented at the same time as objects, more or less, sometime during the 70s. And it wasn't clear at the time what was the difference between one thing and the other, and whether it was the same thing or not. There's a big, in fact, when you learn object-oriented programming, your instructors tend to also not make the distinction very well between the abstract data types and classes. it looks like it's the same. And again, it's not the same. It's really not the same. Abstract data types are a cleaner concept in a way than classes. They're a little simpler. They're basically abstractions of behavior without committing to any implementation. Okay? There's no implementation on abstract data types. Okay? There's just a specification of what are the methods that this object understands. What are the things that this type of object does? And then there can be multiple implementations of this specification, right? So in Java, you have the interface. In Java and C#, the ADTs are in the language via the concept of interface. So here's an interface that extends some other interface, and you define the methods that this does, right? What methods does it supposed to have, but there's no implementation, no details whatsoever, right? This can be implemented in many different ways. So this is abstract data types. This is different from classes. And as you see, some languages made them differently. Not C++. So C++ got caught still in the big confusion of the beginning of what was the difference between, you know, classes and ADTs that looked more or less the same. So C++ doesn't have the concept of an interface. At least last time I checked, although they add so much to C++ that I kind of lost track of the things that they have been adding. But so in C++, if you want to define an abstract data type in C++, the only option is to define a class that is then abstract, meaning that the methods are not implemented. Right? So you can have classes where you define the methods, but then you initialize them to 0 or whatever. I've lost track, or that you basically don't define a body for those methods, and they become abstract. So so this is how we implement interfaces in classes, in particular classes, and those are the ones that have the methods, the implementation of the methods. So classes are not abstract data types. They're not abstract, basically. Classes may be data types, but they're definitely not abstract. So only if they are not abstract, and then you can call them abstract data types. Okay, so another thing that sometimes gets thrown in there and no one really thinks about it is singletons. It's an interesting concept, singletons, which is similar to prototypes, but not quite. So prototypes are objects that carry their own code, right? When you define the object with the fields and the methods as a little capsule. Singletons are a concept that applies typically in class-based languages, so they have classes. But there's only one object, only one single instance of the class. So typically something like this. For example, you have the class foo, and then you have a private static, the instance, right? And then there's no public constructor. So basically you cannot construct an object of this class from the outside. There is, however, something to get the foo, right? And it typically looks like this. If instance is null, then you create a foo, and you can do this because you're doing it inside the class. Otherwise, if it's already instantiated, then you return the instance. So why are singletons interesting in object-oriented programming? So the modern situation sometimes that require just one object of that class. Okay? You could do it with, if you had a prototype language, it would be a good match because it's exactly what it is. It's supposed to be a prototype, just an object that has its own code, and there's only one of those, not many. But when you're using a class that has when you're using a language that has classes, then you have to go through the trouble of defining a class and then saying that there's just one instance of that class. And it's situations where an object is more expressive than the class itself, so it can inherit, override methods, etc. Yes, there was just this was something else that I was talking some other course last week here. Basically, some some APIs provide singletons to you, and you should be aware that that's basically an object that is just one instance of that particular class and not many, for whatever reason. Okay, so now next page, code reuse. Code reuse is another thing that got mixed here in object-oriented programming, particularly with respect to inheritance. Here's an example of a class hierarchy: container, and the subclasses, panels, all panels. That is the typical design. But the important thing that there's two things going on in here. One is the conceptual model, okay, that something is a subtype of something else, meaning that it does the same things, but it does more things, for example, or does something slightly different. But the other thing, besides the conceptual model, it's also a very software engineering reason to having something like this, which is the fact that you can reuse code. Right? If you had a prototype language, or if you have, something that where each class is sort of sealed and you cannot reuse it, then you cannot reuse it. So basically, the idea of inheritance is the idea that you can open up certain modules in your system, in your software system, and you can instead, when you want to add just a little bit more, you can already use the things that you had already defined for that module. So it's code reuse. So and inheritance is a mechanism for code reuse, but it's not the only one. So C++, most languages have just single inheritance. Actually, I think all languages that I know except C++ have single inheritance. C++ is the exception, has multiple inheritance and can be a big mess. Multiple inheritance fell in these views, so it's highly recommended that people don't use multiple inheritance. Can get very confusing very quickly. So, but multiple inheritance means that an object and a class can have more than one parent. All right. So another way of having code reuse, and let me just step back. So the idea is that now we have this concept of objects or classes or whatever, these little capsules of data of implementations, right? Data and methods, and we would like to be able to reuse them some way. That's the idea, because sometimes we want a concept that is sort of wraps around that the concept that we already have, and we just need an extra little layer on top of what we already have. So inheritance is a mechanism for doing that. Another mechanism for doing that is what's called mixins, which is something that exists in Python and some other languages too. It doesn't exist in Java or C#, although C# has something else that Java doesn't have, which I called, I'm blanking out. And I don't remember. I will try to remember by the end of the class. But so mixins is an example of mixins in Python. Basically, it's the idea that you can mix and match these classes, these little templates, right? These little capsules, but not necessarily through inheritance. Okay. So here's an example of a vehicle. All right. Here's the methods, and then these are the subclasses of the vehicle. So car is a subclass of vehicle, boat and plane are all subclasses of vehicle. Okay. And now you have some other class, some radio user. Okay. Mixed in. So this would be a collection of methods or a collection of behavior that has to do with having a radio. Okay, it could be for vehicles or it could be for, I don't know, houses or something like that. Right. So it's so play a song or use the method play song on station. Okay. So these are collection of methods related to having a radio, all right? And so now we can say that the car, this is not inheritance, this is uses this radio user mixin, or basically it has access to this collection of methods that comes from here, right? And so in Python, you can have an arbitrary list here of mixins, right? And so when you do here, self dot something, for example, play song on station, then you are going to access this method that you mixed in the definition of the car class. And one little detail about Python is that in the list of mixins that you put in here, the last one is supposed to be the superclass, right? So all the others before the last one are just mixins. So what that means, it has importance in terms of the type of the object. So this is still of type vehicle, okay? But it has access to all these other little capsules of methods, and so you can mix and match. This is an example of reuse without inheritance. And finally, another mechanism for code reuse is what's called delegation, which was something that was used in some languages, especially the prototype languages, because they don't have classes, so they don't have inheritance. But they're it's a mechanism. It's an interesting mechanism that is similar to inheritance, but it's a runtime. It's a runtime version of inheritance. Which is that the object receives it says, hey, I call foo, and then what's going to do is that it's going to delegate the execution of foo to some other some other object, okay? And then it's up to this object that perhaps it has the foo, or perhaps it delegates to some other object until its foo is found. So basically, you can have a chain of delegations until the method foo is found somewhere, okay? And as you can see, this is pretty much sort of the same picture that I showed you about inheritance a few slides back, but it's all at runtime, right? There's no static relation in here. So at some object, this object gets known, this one is supposed to be a delegate, this one's supposed to be a delegate, and then there's a chain at runtime that gets searched for the method foo. Again, this is another mechanism of code reuse, right? It means that you want to execute the method foo, and you don't need to replicate it everywhere. You have to have it once, and then as long as you have this chain of pointers that lead you to that method, then you find that method, you can execute it. And this leads me to Ruby, which is a very dynamic object-oriented language. It's like radically object-oriented and radically dynamic. I mean, it's a really nice language. It's very simple. The object model is really, really simple, which means that everything is an object. And everything being an object, it's accessible to the programmers too. It's not hidden. The fact that things are objects, everything is an object, is actually shown to the programmer. And so every object has a pointer to its class. A class is also an object. It's represented by a class object. Every class object contains a hash table with the method names and the code. Every class object has a pointer to its superclass. And then, so the method dispatch is a lookup for the applicable method starting in the object and just moving up the chain. And if you hit the top without finding it, then you get the message not understood, like you used to get in Smalltalk. But all of these pointers, in a way, are changeable. That's the interesting thing about Ruby, because everything can be programmed by the programmer. So let me talk now about dynamic dispatch. Let me see what else I want to have on this slide deck. Right. So dynamic dispatch is something that you may be familiar with or not, but it's the idea that when you call a method on an object, that method may not be known at compile time. Even if you have a compiled language like C# and Java, C++, that particular method, the function that is being called, most generally cannot be known at compile time. It can only be known at runtime. And maybe you know about this, but maybe you don't. So I'm going to talk about this because it's an important thing about object-oriented programming languages. Especially the typed ones, the ones that have types. So delegation, Aditya sent a chat. Delegation is a design pattern. Yes, delegation is also a design pattern. And some languages have that embedded in them. And some of these important chains of links between parents and children and the delegates. JavaScript brought some of that back. I will talk more about JavaScript next class. But yes, it's also a design pattern. So Java, C++, and many others are strongly typed. And the purpose of the type system is to prevent certain kinds of runtime errors by compile time checks. Okay, that's the purpose of runtime system. So the usual guarantees is that the program execution will not send a message that the receiver doesn't understand. Okay, so that's the idea, that in Java and C++, if you call a method, and that the existence of that method is checked at compile time by the compiler, right? You don't get method not found at runtime in Java or C# or C++. You get that in Ruby, or in Python you also get that. So in the dynamic languages you get that, but in static type languages you don't get that. The idea is that you can verify that the methods that you are calling actually exist. Or that you send a message with the wrong number of arguments. But usually, unfortunately, most object-oriented languages have the problem of the null. They don't check if it's null. The object is, at compile time, you cannot check if it's null. It's a pain in the neck. Anyway, so typing. So what's the thing about typing and dynamic dispatch? So the type system allows us to know in advance what methods exist in a class, right? And the potential types for the object. So they are declared in the static type via the class, and also via the class inheritance, so the super types. But we don't necessarily know. Do I have an example in here? Right. We don't necessarily know exactly which method is going to be executed, because if you have a hierarchy, a top class, and you have two instances, two subclasses of the top class, right? And they all have a method called foo, right? But so there's a foo method defined on the superclass. There's a foo method defined on one of the subclasses, and there is no foo method on the other. So the second subclass inherits the foo method from the top. If you have a method, some other method somewhere that receives an object that is declared to be of the super type of the root of this hierarchy, then you don't necessarily know which method is going to be called when you call foo, because it depends on the particular type of that particular object that gets sent on that method, right? If it's the type that has a redefinition of foo, then it's that particular method. So I'm saying that the method called foo can have many implementations throughout the hierarchy, and it's only at runtime that you find out exactly which of the implementations you're going to call. That's what's called the dynamic dispatch, that you cannot resolve the exact method at compile time. You can make sure that there is a foo method, okay, but you cannot know exactly which one of them if there are many. So whenever we execute this, we know the class of the object, we know what field it contains, we can guarantee that the initial part of the subclass object matches the layout of the one in the superclass. This is coming from here. We use this to engineer fast dynamic type lookups. That's what I'm trying to get at. That the way that compiled languages do objects is they do it to try to make that dynamic dispatch very, very fast. And so we know how the size of these objects exactly. And so we know the size of the classes too. So we can offset the inherited fields so that we know exactly where to go when we need to go to the superclass. Okay. So, right. So these things are actually easier to understand in dynamic languages, although compilers try to optimize. The dynamic language is much easier to understand. So in Ruby, an object contains a pointer to a paired class data structure. And this is where the methods are stored. Right, so this is a table of pointers to the appropriate methods, or so that it's called the virtual function table, the V table. And the method calls are indirect through the object's class V table. So something like this, I already showed you this. Basically, the classes are basically data structures that contain the lambdas, the functions themselves, right? So that's the idea. And in Ruby, it's very obvious and very explicit that the classes are objects too. Okay, in languages like Ruby, that is sort of people know that everything is an object, including the classes. The classes are also objects and they can be accessed. But in Java and C#, this is also true. Okay, classes are also objects. We cannot manipulate them as much as we can the class objects in Ruby. In Ruby, you can actually change them at runtime. You cannot do that in Java or C#. You cannot change the classes, but they are objects too. And we'll see more about that next week when I talk about reflection and how these structures can become available to programmers in languages that are a little bit more restrictive than Ruby. Right, so some details of how to make overriding and inheritance work fast in compiled languages. But let me move on to the self-reference, because this is more interesting. I mean, you may want to try the extra credit this week. So in Java, the this is the self-reference, where you have the this. In Python, you have self. But I don't know how many of you have noticed that things in Python are a little different. They look similar to Java, but the details are very different. So the first thing that you will notice when you're writing a class in Python is that there's always a first argument to every method that is supposed to be called self. Okay? And I don't know how many of you know this, but actually self is not a reserved keyword in Python. Did you know this? It's not reserved. It's just a regular variable. It's just a convention. There's a lot of conventions in Python. So anyway, but whenever you are defining methods of a class in Python, there's always this self, which is not true in Java, right? So in Java, there's no this. This does not come as a parameter. This just magically exists in Java and C# and C++. In Python, that particular magic doesn't exist. So at least the self is explicit, okay, when you declare the method. There is, however, another magic that can be very confusing, which is that when you instantiate a point object, this is equivalent to new point in Java, C# and C++. And then you call a method. When you actually call the method, you don't send any argument as the first argument. So you say p.print, And print is defined to receive something, and you don't send it something. That is the magic. On the one hand, they kind of got rid of the magic on the definition of the methods, but then they added the magic on the invocation of the methods. So it's still confusing. So where is this self, right? What is this self, and where did it go? So self is not the reserved keyword. Python methods are class-level functions that take an object as its first argument. So this is very clear that this is basically functions. All of these things are functions that take an object as the first argument, an object of this type as the first argument. The object is passed implicitly, but received explicitly, okay? And so basically, if you have something like this p.print, this is just what's called syntactic sugar for the real thing. And what is the real thing? It's this, okay? The name of the class dot the name of the function, and then give it the object that you want to pass it, okay? This is the real thing. This is just syntactic sugar for this. This is to make it more similar to what people were used to in object-oriented languages, okay? But in reality, what these methods are, they're just functions defined within the scope, right? The point scope. And you have to, you pass it some object that then is called self. Okay, this binds to self, and then that, voila, this is where self comes. Something similar happens in the other languages, in Java and C# and C++. We don't, since we don't see it, we think that this is here, and we just don't think much about it. But underneath the hood, something very similar to Python. This is what's going on in the other languages too, because there's no magic, right? There's only the appearance of magic, but there is no actual magic. These variables need to come from somewhere. So there's also a lot of magic in JavaScript, including for the self-reference that I will explain a little more on about JavaScript next Thursday. However, I want to stop on this slide about Python, because if you want to try for the extra credit at 13.3, you need to pay attention to what Python does, because if you want to bring the self-reference, you are going to have to do something like this, okay? And this is as much as I'm going to tell you. So pay attention to what Python does, because Python kind of removes the magic, and you need to do something like that too, for having some sort of a self-reference.